All right. What is up, everybody? Tom McGurl here again for another night of learning Rust. Tonight we're going to be picking up on chapter 13. I'm excited for it. We're getting into a little more of the functional programming aspect of Rust, which I'm all here for. I mean, I love functional programming, as you probably have heard me say many times. So it's going to be a fun time. We started it last week, and we will be continuing from there. All right, it's time for the usual plugs. Ready? Are you ready? If you missed any of the past videos, don't worry. They're all posted here. It's easy. We got all the parts when we started the book from chapter 1 all the way up to chapter 13. We wrapped up chapter 12, which was a lot of fun. We built a grep clone, so check out these two if you're just interested in that part. Super cool. We also got some one-off content, such as building a development environment for Rust with Docker and Docker Compose. If you're interested in building a serverless API with AWS Lambda, DynamoDB, TypeScript, check it out. It's all there if you wanted to catch up. If not, if you're just hopping in, just want to check things out, that's cool too. But of course, on YouTube, you can watch at 1x, 1.5 speed, whatever you want. Check that out. Here's the Twitter if you want to get updates for when I go live. You can also get that on Twitch. If you're interested, you can follow on Twitch. And more importantly than both of those, for those following along, is the GitHub. This is where we'll be pushing the code for everything we do here. If you are following along yourself, you probably have your own repo. But if you wanted to jump in and catch up without worrying about writing all the code for the past chapters, you can pull that down. You can go through the commits even if you'd like and see what we did for each chapter. All right. That's all, folks. Now we're back to the content. So as you know, if you've watched these videos before on YouTube or you've been part of the stream, you know we always give a shout out. We got to do it, right? We're so grateful for these folks here, Steve Klobnik and Carol Nichols, and anyone from the Rust community that contributed. Without their efforts, we would not have this book to learn Rust. We'd be going at it. If you guys know me, I'd be jumping right in. I'd be trying to jump right in, trying to code stuff, and I'd be like, it's not working. I'll just put an asterisk. That'll do it. Not going to fly. I found that out pretty quickly. Not going to fly with Rust. I got to understand these concepts. And even after learning a lot of these concepts, right, there's so many, I still have some trouble when I'm just trying to dive in. So I have to go back and reference my notes, or if you were, or my code, my repo, right, that we've been working with. So that's been really awesome to have that code as we go through. And, you know, we did last chapter 12, we did a little program. So we got to leverage those skills that we learned. And we're going to do a little more of that. So, again, thank you to Steve Klobnik, Carol Nichols, and anyone from the Rust community that contributed to this book. Super, super appreciated. Couldn't be doing this without you. So awesome stuff. And it's been a lot of fun so far, right? I've been enjoying it, so I hope you have as well. All right, so today we're going to be picking up where we left off last week in chapter 13. I'll do a quick catch up just because we weren't that far into the chapter, so it shouldn't be too big of a deal. But we did cover some really, really awesome stuff, so we don't want to skip it. So this chapter is all about closures and iterators, and we started out learning about closures and how they can encapsulate values. So they're either lambdas or functions that encapsulate values. And so what we did, let me just scroll down to where we left off, and then I'll show the code. So we left off somewhere around, let's see if I can find it, cacher. So we're using cacher, that's for sure. And we did it, yes, where we were trying to modify it. All right, so let me pull up the code and we'll have a better sense of what's going on. So we built this fake program. It was like kind of like a fake program. What up, Kiwi Gomer? Oh man. All right, let's see if I can do this. Kiwi Gamer Romania. What up? Thanks for the follow. Welcome to the stream. So last time we started building this mock program that generates a workout. You give it an intensity as an input and a random number, and it figures out a cool workout for you. And a lot of it was hard-coded as part of the tutorial, but we're going to quickly see that it wasn't about the program, it was more about the concept. So Kiwi Gamer in the chat says, I have no idea in Rust. Kiwi, that's totally fine. We got you covered. You can follow along. You just started chapter 2. Awesome. If you check out the YouTube above, you'll notice we have videos for all the chapters, so you can watch those and follow along. But if not, just sit back, enjoy. Maybe you'll pick up some of the context. Maybe the content will make sense, maybe not. But happy to have you here either way, and I'm glad you started your Rust journey. That's fantastic. Chapter 2 is a good chapter. Build the guessing game. We really enjoyed that. So basically the general idea here of why we use closures was we had a lot of these calls to a function that computed an expensive result. And so what we wanted to do is create a closure. And more importantly, we wanted to memoize the function. And that's what we ended up doing. We created, if you're familiar with memoization in either JavaScript or Python, you can do it there, right? Java, you have like lazy evaluation. Memoization is the idea that when you call a function with a value, it will memoize, it'll remember, right, or take note of that value and that response, right, the result of running the code with any given inputs. And it will memoize that so that if it's called again with those inputs, it will just return the cached result. If it's given new inputs, it'll run it again. Now, memoize a function, you need to make sure that the function you're memoizing is a pure function. What do I mean by that? I mean that it's a function that if you give it the same input over and over, it will always return the same output. There are no side effects. There's nothing in there that is based on something that changes, right? That is atomic. So you're not going to have something like a function that calculates the time and adds that to a number, because that's going to be different, right? That's not a pure function. Pure function, you can think of something like add, right? It takes A and B and it always returns the sum of A and B. Something that, given the same inputs, will always return the same outputs no matter how often it's called. And because of that property, we can memoize that function. We know that if you provide 5 and 5 to an add function, it's always going to be 10. So if we see those arguments, we can store that result and return that same result back. Now, is it practical with a simple function such as add? No, but it gets practical when the functions are doing a lot of heavy computation. Maybe they're parsing over a lot of lists. Maybe they're doing some heavy processing. Maybe they're trying to find a nth prime number, whatever it may be. Usually it's something where you're parsing lists and doing some sorting or filtering, right? Those functions can benefit from memoization because they'll only do that expensive computation once, right? And if you give it a different output, it'll notice that it doesn't have that cache result and it'll run the function again. And so we wrote our own memoizer or our own lazy evaluator. And the way that we did that with Rust is we actually used a struct, and we called that struct cacher. And so cacher, we made it generic over type T, and it basically, the type was, it had to be a function. In this case, it had to be a function that takes a unsigned 32-bit integer and returns an unsigned 32-bit integer. We're going to modify that in a little bit. You'll see they're going to actually have us try to make this a little more generic. And we have two things, right? We created a new function for instantiating a cacher, and we created a value. And so when we instantiate the cacher, we have two things, right? We give it our value, which is it'll hold the value, basically the result of calling a function in a certain way, and a calculation, which is a function to be run, right? And so what we would do is when we try to access a value, so in this case you'll see here, we define expensive result, and we create a new cacher, and we give it a calculation. Our calculation is just number, and what does it do? It prints, it sleeps for 2 seconds, and returns that number, right? And so what we do is when we call this function, we ask for the value and we pass the intensity. What it's going to do is it's going to say, hey, do I already have a value stored for that intensity? If not, it's going to run the calculation function, passing it this intensity argument, and then it's going to store the result for future calls to be easily pulled. And how does it do that? Well, we're using a hash map. And so what we do is we have a hash map. When you call it with an argument, it creates a key for that argument and stores the result of running the calculation with that argument as the value. When you call it, it'll check the hash map to see if it already has an entry for that argument that you passed. If it does, it just returns it. If it not, it runs the calculation. And so here we had an example where we have this generate workout function. If the intensity provided was less than 25, it asks you to do these two things. And because we're passing it the same intensity, you'd actually only see the computation of the function run once. Here, it wouldn't run at all. And because it's lazy evaluated, we don't even waste calling it once. And here it would only run once. So that's kind of the general idea of where we left off. Again, it'll be on the YouTube video from the previous week, which of course you can always find right here. It'll be on this one here, part 17. That's where we started that. So today, what it's asking us to do, basically we left off at this part. We modified cacher to hold a hash map rather than a single value. The keys of the hash map will be in the arg values that are passed in, and the values of the hash map will be the result of calling the closure on that key. Instead of looking at whether self.value directly has a sum or a none value, the value function will look up the argument in the hash map and return the value if it's present. If it's not present, the cacher will call the closure and save the resulting value in the hash map associated with its arg value. Kiwi in the chat said, I have been focusing mostly on math and physics recently, but I also want to learn algorithms, data structures, and some backend for websites. And Rust can do all those. Yeah, so Rust is very versatile. With WebAssembly, you can write, you can compile to JavaScript, do some web stuff. Of course, you can write systems programs. And yes, there are, in fact, web frameworks for Rust. Also, if you're trying to learn something that can cover all, the back and the front end, another popular language has been JavaScript, which can run on the front end. It can run on the server. You can write apps with it. So another fantastic option. But yeah, this stream right now, we're all about Rust. I come from a JavaScript background, but we're diving into Rust, and I'm using that kind of background to help me figure things out. But really enjoying Rust so far. So definitely a great language to learn. And thanks for being here again. Okay, so now we did that modification. We used the hash map, but then it asked us to do something else, which I'm excited about because we're going to be able to leverage some of the knowledge we used in previous sessions, if you will, which is we're going to make it a little more generic. So check this out. The second problem with the current cache implementation is that it only accepts closures that take one parameter of type unsigned 32-bit integer and return an unsigned 32-bit integer. We might want to cache the results of closures that take a string slice and return usize values, for example. To fix this issue, try introducing more generic parameters to increase the flexibility of the cacher functionality. Now, what does that mean? It means we need to make that calculation function a little bit more generic. So let's see what we can do there. So let's take a look. The function, right? The function signature right now is, of course, unsigned 32, unsigned 32. Now, we've dealt with functions that can take either an unsigned 32 or a usize, and we've dealt with them using generics, right? And we have some generic happening here, right? But we can do a little bit more, right? We can create fn of t, right? We can specify that the generic has to implement a particular trait and so forth. So let's see how we can make this work with generic. So what we'd have to do is this function value would also have to be generic, right? Because it might return something different. So what I'm going to do is I'm going to actually pull up our notes from some of the previous chapters. So here we can go here, where we have our different chapters, and here we have generic types. And so here is an example of some generic types. So we have one example is a point, right? So this is generic, and it has two things inside of it. This is generic of two different types. And so here we have, we can create a point of an F32. So we could create a structure that holds many different types, right? So we could say, hey, this structure, memoizable, right? It can be a usize or an unsigned 32-bit integer. But we'll try to figure out the best way to do that. Kiwi in the chat said, wants to get used to low-level languages. Yeah, low-level languages are a fantastic thing to learn. Fast, that's why we're learning Rust, right? I wanted to get experience with the systems programming low-level language. So definitely a good thing to learn. And you also asked, what could I use to learn some JS libraries and frameworks? Fantastic question. So one of my favorite tutorial sites is egghead.io. Awesome site I use myself. They have a lot of free content. I used to use scotch.io. I'm not sure how much they've done, but I also like to just look at tutorials on dev.to, which is a fantastic website. I occasionally also will putting up some JavaScript stuff. So I have one series on creating a React Native app with JavaScript, and I plan on doing more. But yeah, YouTube has some fantastic stuff. Highly recommend Egghead, and definitely just some articles on dev.to. There's some really fantastic stuff if you search for tutorials. And these people are out putting out free content, and I've consumed a bunch of it. So it's awesome. There's a lot of stuff out there. But yeah, I'll put a message in the chat too with some cool links to stuff. All right, so we want to make it generic. What else can we do? So let's look at some other functionality where we have generic. So here we have largest that accepts a T, and we're saying it should implement partial ordering, right? Because we're doing comparison. So maybe we want to do something like that. But so what we'll do is we're going to say, we want to say that our function, our Lambda function, takes a generic. And so we're going to need to leverage T here. So something like this, right? And so let's try messing around with it, and I'm sure the compiler and the Rust analyzer will give us some cool hints. So let's see what happens if we just change this. We say T. I want to see what kind of errors it gives us. So it's still loading. Loading. Okay, it doesn't like that. Hold on. Let's see if we can get the Rust analyzer to load up. Loading. Okay, I'm going to close this because it looks like my Rust analyzer is not working there. Let's see. Loading. Weird. There we go. Perfect. Okay, so we have our Rust analyzer. So you saw a lot of stuff popped in. That's Rust analyzer running. It gives us those type hints. Okay, so let's see how we can make this generic, right? We wanted to take a generic type. And so we've seen, like I said, we've seen generic function signatures. They look something like this. Right? So let's try, see if we can do something like that. So maybe we have to do it like this. And let's see what it's going to tell us. So it says, syntax error, unexpected item. What if we do, let's see. Here we're saying function. Here's another, let's see, where's another generic function? Largest. So we put the signature here. And here we put, okay, so let's see if we can do function T. And we can call this arg, and we'll say it's of type T. And we'll return something of type T. Let's see what it complains about. Syntax error, unexpected paren. All right, so let's see if we can look at how to define. Oh, sorry about that. All right, let's see if we can look at how to define a generic Lambda type like this. So one thing that's worth noting, this signature here, which we've talked about in the book, I'll pull that up. That's up here where we have, let's see. The caster struct has a calculation field of the generic type T. The trait bounds on T specify that it's a closure by using the function trait. Any closure you want to store in the calculation field must have one U32 parameter specified within the parentheses after fn, must return a U32. So it says here, note, functions can implement all three of the fn traits too. If what we want to do doesn't require capturing a value from the environment, we can use a function rather than a closure where we need something that implements a function trait. Okay. All right, so let's see what we can do. So we need to be able to modify this. So here, I'm going to put this over here, and let's see. So I tried doing, so this is the current signature. So I tried doing something like T. It doesn't like that. So what if we did arg T? Oh, well, also it's not going to like that because we're already using generic T. So what if I did U? U. All right, so it doesn't seem to like any of these. So what I'm going to try to do is, let's see how we specify this. So I'm just going to search for it. So let's do search for specify generic closure Rust. Does Rust support closures with generic return types? For example, I want to write something like this, but the syntax is clearly wrong. So this is very similar to what we're trying to do. No, as far as I know, you can't. I mean, you can define a generic closure. What you can't do is create a binding with a generic. Okay, so fn get T. Okay, so here. Let's go back. I'm going to try to search for call generic closure with concrete type. Let's see, Rust generic closure signature. Where, okay, here we go, FNTS. So it looks like, okay, so maybe we can do something where we just define it like this, where we say it takes the type U and returns a type U. And I wonder if we have to specify, yeah, let's see what it says about specifying U. A type parameter with a similar name exists. Cannot find type U in scope. Similarly, type parameter T defined here. A type parameter with a similar type exists. Okay, so let's see. Maybe we can do, what happens if we do this? So this says now, same thing. Cannot find type, oh, U. It's looking for U. Well, now it's just stuck. All right, let's do this. Let's try. Oh, wow. All right, let's go back to what we had. Looks like my analyzer is stuck in a bad state. Let's close this file out, reopen it. All right, so what I'm going to do is I'm going to run cargo run. All right, so that's, it worked. So it's just for some reason my analyzer is messed up. Let's see if I can refresh this here. No, I don't want to do that. Rust analyzer. All right, weird. So not totally sure how to do this one. So what I'm going to do is I'm going to search it. Let's see if we can find some help. And if not, we'll move on to the next step. Creating cache for closure with generic type. So we found some Rust help here. So here they're doing, let's see. So this is how they're handling this part. So they have implementation TKV, so they've created different generic types here. T is a function K that returns a type V. Pretty cool. This is awesome. All right, so I'm not going to try to dive into that because I want to go back and learn a little more. So what we're going to do is we'll continue on and we'll come back. All right, so what's the next step if we were to skip that for now? Let's see. All right, here we go. Close that. Open that back up here. There we go. All right. Let Rust Analyzer kick in. Okay, so the next step, let's see. Capturing the environment with closures. All right, let's see what this is. In the workout generator example, we only use closures as inline anonymous functions. However, closures have an additional capability that functions don't have. They can capture their environment and access variables from the scope in which they're defined. Listing 13.2 has an example of a closure stored in the equal to x variable that uses the x variable from the closure's surrounding environment. Okay, so let's create a separate one here. So I'm going to create another file. Let's see, what is this? Iterators and closures. So let's do this. Let's create another. Let's move this to another project. This way we have two. So what I'm going to do is I'm going to create a new project. So I'll do cargo. First, let me create a directory. We'll call it cacher, and we'll move this stuff into there. So we'll move cargo.lock, cargo toml, cacher, the source and the target. And we'll move that into cacher. There we have cacher. Great. And so I'm going to do cargo new, and we'll just call it examples. Okay, can't use that, so we'll do cargo new closures. That should work. Yep. All right, so let's do code closures. We'll open that up here so that Rust Analyzer can work correctly. All right, and here we have our main function. So here we'll copy that code that they have there. So let's try it out. So let's see. So we have let x equal 4, right? And then we're going to do let equal 2x equal, and this is going to be a closure here, right? Z equal x. So again, what this is going to do is it's going to capture or enclose the value of x. So this will forever be 4, right? And then what we'll do is we'll say let y equal 4, and then we'll assert equal to x, y. And we can just run it right in here in the book. That's the beauty of this. It's pretty cool. Here, even though x is not one of the parameters of equal to x, the equal to x closure is allowed to use the x variable that's defined in the same scope that the equal to x function itself is defined in, right? It's in the same scope, so we can close that, which is pretty cool. We can't do the same with functions. If we try the following example, our code won't compile, so it has to be a closure. What's the difference between a closure and a function? Well, it's a signature, right? We learned that. It's these pipes. So you couldn't do this down here. And so if we run this, it works just fine. However, if we were to change it like they have here, we'll see that it won't work. So let me comment that out, and we'll do function equal to x, and I'm sure they'll tell us before we even get a chance to try running it. You can see right here, can't capture dynamic environment in a function item. Use the pipe closure form instead. Check that out. Look at that, right? That's why I love this. Rust is fantastic. Look, it tells you right there. If you were trying this out on your own, it tells you right there, you know, what the problem is, and you can peek it. It pulls it right up, points to the code. So really, really fantastic stuff. Definitely use the Rust Analyzer if you are using Rust with VS Code. It's been phenomenal. So very cool stuff that they show you that right there, so you don't even bother trying to compile it. But so pretty cool. The compiler even reminds us that this only works with closures. See, they say it there. They actually tried to run it and compile it so you can see it in the compiler. When a closure captures a value from its environment, it uses memory to store the values for use in the closure body. The use of memory is overhead that we don't want to pay in more common cases where we want to execute code that doesn't capture its environment. Make sense? So let's read that again because that's important. When a closure captures a value from its environment, it uses memory to store the values for us in the closure body. So it's a little more overhead that we wouldn't want to pay in common cases where we would execute code that doesn't need to capture the environment, right? Code that could just take arguments. Because functions are never allowed to capture their environment, defining and using functions will never incur this overhead, right? You can guarantee it won't. Closures can capture values from their environment in 3 ways. So these 3 ways directly map to the 3 ways a function can take a parameter: taking ownership, borrowing mutably, right, in a way that you can mutate it, and borrowing immutably. These are encoded in the 3 function traits as follow. So there's the 3 traits. Function once consumes the variable it captures from its enclosing scope, known as the closure's environment. To consume the captured variables, the closure must take ownership of these variables and move them into the closure when it's defined. Pretty cool. The once part of the name represents the fact that the closure can't take ownership of the same variable more than once, so it can only be called once. So that's important, right? Then we have the function mute. So function mute can change the environment because it mutably borrows values. And then function borrows values from the environment immutably, so in an immutable way, right? And so we have these lambdas use that fn, right, which we saw. So pretty cool. All right. When you create a closure, Rust infers which trait to use based on how the closure uses the values from the environment. All closures implement function once because they can only be called at least once. Closures that don't move the captured values also implement function mutable, and closures that don't need mutable access to the captured values also implement function. So pretty cool. So they all implement function once. In listing 312, the equal to x closure borrows x immutably. So equal to x has the function trait because the body of the closure doesn't need to mutate the value of x, and it only needs to read the value. If we want to force the closure to take ownership of the values it uses in the environment, you can use the move keyword before the parameter list. So if we need the closure to take ownership of the values it uses in the environment, we can use the move keyword before the parameter list. This technique is mostly useful when passing a closure to a new thread to move the data so it's owned by the new thread. So it's useful when you're passing around that closure. We'll have more examples of move closures in chapter 16 when we talk about concurrency, right? Because we're going to move stuff into threads. We've seen that a little bit when we did the rustlings. For now, here's the code from listing 1312 with the move keyword added to the closure definition and using vectors instead of integers because integers can be copied rather than moved. Note that this code will not compile yet. So let's just read that one more time. So here we say, with the move keyword added to the closure definition and using vectors instead of integers because integers wouldn't require the move integer because they can be copied rather than moved. So we're using a vector just to make it a little more complicated so that we're actually going to touch upon something that actually has borrowing, right? Integers wouldn't deal with it because they get copied. All right, so let's comment this out. All right. And we'll create a vector, vec 1, 2, 3. Let equal to x equal move z equals x. And then we're going to print ln can't use x here. And then we're going to print the debug there, x, and then let y equal vec 1, 2, 3, assert equal to x, and we're going to pass it y. So it's printing this here because we can't move it. So basically it's just saying that we've moved x's value into this function, and so we can't use x in this context anymore, right? It's moved into that function. And so let's go ahead and run this. Oh, what did I mess up? Let's see, what does it say here? Expected one of, oh, did I leave off a semicolon somewhere? We have equal to x equals move zx. No, that's right. This is right. This is fine. This seems fine. Let's see. What's happening here? Back 1, 2, 3. Okay, there we go. And so here you see borrow of, you can see right here, I don't even need to compile, borrow of move value x, right? Value borrowed here after move. Value moved into closure here, and it gives you the line. Variable moved due to the use in closure. Move occurs because x has type standard vector, which does not implement the copy trait. That's why we used vectors instead of integers for this. So pretty cool. And you can see here, if we try to compile, we'll get the same thing. So the value of x is moved into the closure when the closure is defined because we added the move keyword. The closure then has ownership of x, and main isn't allowed to use x anymore in the println statement. Removing println will fix this example because the scope won't be trying to use it. Most of the time when specifying one of the trait bounds, you can start with function, and the compiler will tell you if you need to implement function mute or function once based on what happens in the body of the closure. So that's pretty cool. To illustrate situations where closures that can capture their environment are useful as function parameters, let's move on to the next topic, iterators. We've done some, right? We've done some iterators. We did like a reduce, if you remember. We used a lambda like this. So this is going to be pretty interesting. I'm excited to see it in action. Sorry, I'm just cleaning my glasses real quick. It's getting steamy. We're all learning all this Rust in here, you know, Rustations. All right, let's check it out. Next chapter, processing a series of items with iterators. So this is what low-key, this is what I've been waiting for a while, right? I'm ready. I'm ready for iterators. I'm ready to pass it some closures. You know, and you might be looking at this stuff and saying, this is familiar. And that's great. It should be ringing a bell. If you've come from a language like Python, you're looking at lambdas, right? If you come from JavaScript, you're like, this is very familiar, right? Because we deal with functions and passing functions all the time. Sometimes you have arrow functions, right? Sometimes we call them anonymous functions, whatever it may be. This is a common concept in functional programming, right? Passing functions. We call it functions as first-class citizens. It's a weird, naming for it, but whatever. Processing a series of items with iterators. The iterator pattern allows you to perform some task on a sequence of items in turn. An iterator is responsible for the logic of iterating over each item and determining when the sequence is finished. When you use iterators, you don't have to implement that logic yourself. You don't have to re-implement. So an iterator, right? You could have, check this out. Low-key, I'm just trying to flex about my tech decks. But let's say you have an iterator that iterates over the tech decks, right? It'll iterate 1, 2, 3. Yes, I have 3 tech decks. Low-key flex. It's a low-key flex, but it's pretty cool. But so what we're going to see is iterators will allow you to perform a function, right? You give it a lambda or a closure, what we're calling it in Rust, and let's say the closure's all it does is flip it. Given a tech deck, it flips it, right? So we can iterate over the list and apply that function to each item. So grab a tech deck, flip it, right? Grab a tech deck, flip it. Grab a tech deck, flip it. Again, just a low-key flex. I'm just trying to show how many, was trying to find any excuse to show you how many tech decks I had. One day maybe we'll skate on stream, who knows? Might get weird, who knows? But so that's what the iterator is gonna do, right? So in Rust, this is gonna be key. I can tell it's gonna be key because it's italicized, right? You saw that coming, you saw that lazy word, italicized, it's gonna be key, right? So in Rust, iterators are lazy, meaning they have no effect until you call methods that consume the iterator to use it up. For example, the code in listing 1313 creates an iterator over the items in vector v1 by calling the iter method defined on vector over generic type t. This code by itself doesn't do anything useful. So let's look at it. In fact, we're gonna write it. So let's do this. So first I'm gonna get rid of this so this actually compiles. And I say let v1 equal vec 1, 2, 3. And then we'll do let v1 iter equal v1 dot iter. All right. Once we create an iterator, which we've done here, right? We created an iterator. We can use it in a variety of ways. In listing 3.5 in chapter 3, low-key back in the day, we did that, right? We used iterators with for loops to execute some code on each item. So we looped over for each and executed some code on each item. Although we glossed over what the call to iterator does until now. So back then, you remember we were young gods, we were coming in strong, we were like ready to learn Rust, bright-eyed, like children coming in, like trying to be Rustations. And we were reading about this and it was probably said something like, you'll touch upon that in chapter 13. And back then, we didn't even know if we'd make it this far. But I remember, we'll go back and watch it. I promised you. I said, we're going to get there. One day we're going to be at chapter 13 and I'm going to come back and I'm going to talk about how we made it all the way to chapter 13. Just look at us. Where are we, right? Right? Chapter 13. Here it is. Now it's talking about back in the day, like it was like years ago. Chapter 3, right? So we did it, but now we're going to find out why. So the example in listing 1314 separates the creation of the iterator from the use of the iterator in the for loop. So it separates it out. Pretty cool. So let's take a look. And you remember, I'll show you how we did it before. So this is how we're doing it now. We're saying for val in, right? We're going to just print ln because we want a new line. Got and it'll print the value. And let's run it. Let's just run it so we can get some use out of it. I'm gonna get out of your way really quick. I'll run it for you. Yeah, I flipped. It looks weird. I get it. All right, so I'm gonna run cargo run. There, so we got 1, 2, 3. Pretty cool, right? Okay, so this looks familiar, but actually what we used to do is we used to not create this, right? We wouldn't do it separately. Before, what we were doing is we would just do this, right? Just do it in line. But yeah, it doesn't really matter. This is just illustrating that can be created separately and it's not consumed until it's used, right? So that's pretty cool. All right, so we separated that out. In languages that don't have iterators provided by their standard libraries, you would likely write the same functionality by starting at a variable index 0, using that variable to index into the vector to get a value, and incrementing that variable value in a loop until it reached the total number of items in a vector. What are we talking about here? We're talking about for loops, right? If you've used Java, JavaScript, you've used for loops. We can do one really quick here. I'll just pull up the trusty. I've actually never used the inspector in Microsoft Edge, but yeah, it's Chrome based, so this makes sense. So I'm going to pull up the console here, and we'll write a basic for loop. So what a for loop would look like in here, and it's not going to look nice because the new line, for let I equals 0, right? While I is less than 4, I plus plus. And what would we do? We would do something. So we could do, we would probably use it to get the index of something. So specifically, let's say var, let's say const my list equals what up Twitch. And YouTube, what up? So we'll do what up Twitch and YouTube, pop that on there. And we'll do while it's less than 0, 1, 2, 3, 4. We'll do while it's less than 5. But what we can actually do is mylist.length. And we'll print something out. So this is just a basic for loop. This is JavaScript, but you get the idea. What we'll do is we'll do console.log mylist I. So this is how you would do it without an iterator. Run it. What up, Twitch and YouTube? Pretty cool. So this is it. This is what they're referring to when they're talking about using an index. Of course, in JavaScript, we don't need to do this anymore. We could do for each, right? So we could do mylist list.for each. We give it a function. What is the function? Console. The function takes a item and does console.log item. We could also just console log itself is a function that takes something, so we could just do this, right? Adds a little more to it, but you get the idea. Okay. Anyway, no. I lost it. All right, we're back. We're back. All right, let's put this over here. No, stop. Go over here. What are you doing? How do I move this over here? There we go. Let's make it full screen and then we'll make it side screen. Perfect. No, it's still not half. Hold on. Let me make it half the size. Why isn't it doing it? Oh man. Oh, you know what? It's because I resized it myself. Hold on. Let me just fix this here for you. Okay. There we go. All right. Still not centered. There we go. So that's how you would do it. And here they have, let's see, we lost it now. I lost it. Okay, we're back. We're back. We're back. In languages that don't have, we would use index. Iterators handle all that logic for you, cutting down on repetitive code you could potentially mess up. Iterators give you more flexibility to use the same logic with many different kinds of sequences, not just data structures you can index into, like vectors. Let's examine how iterators do that. So it's going to allow us to use the same functionality, the same kind of code, right? The same patterns and syntax for not just vectors. And that's important. That's going to be great, it's going to add a good experience for us when working with different data types. Okay, so let's try this. The iterator trait and the next method. All iterators implement a trait named iterator. Again, we're familiar with traits. We learned about the copy trait, right? The partial order trait. We know about traits. This one's named iterator, and it's defined in the standard library. The definition of the trait looks like this. So here's the definition. It's a public trait, type item, and a function next. So next returns an option generic over the type item, because there may or may not be a next. Notice this definition uses some new syntax, type item and self item, which are defining an associated type with this trait. We'll talk about associated types in depth in chapter 19. For now, all you need to know is that this code says implementing the iterator trait requires that you also define an item type. And this item type is used in the return type of the next method. In other words, the item type will be the type returned from the iterator. Makes sense. Looks easy to read. Nice and clean. The iterator trait only requires implementers to define one method, the next method, which returns one item of the iterator at a time wrapped in sum, and when the iteration is over, returns none. We can call the next method on iterators directly. Listing 1315 demonstrate what values are returned from repeated calls to next on the iterator created from the vector. Okay, so next, right? Let's read that again. It's important. When we call the next method on iterators directly, so that's what we're seeing here below. But so it only requires we implement next, which returns one item of the iterator at a time wrapped in a sum. So that's important. It's wrapped in a sum, right? Because it's going to be an option. Option, right? Sum or none. Okay, so let's see this down here. So let's write this. We'll create this function. Go down here. Actually, we'll go at the top. Let's go at the top. Function, iterator, demonstration. I like that. That's usually what we name our stuff. So, and we have a test. So we're going to do test. And so we'll do let v1 equal, again, it's just a vector. We're going to put 1, 2, 3 in it. Not very creative, whatever. And then we're going to create a mutable v1 iter. So mutable iterator equals v1.iter. Create that iterator. And then we're going to assert equal. I'm not going to write all this. I'm going to copy it. And we'll just see what's going on here. So what's going on? All right, so here's what's going on. Sorry, my formatter's all fucked up. Messed up. So assert equal v1 iter dot next, right? So here we're asking for the next value, and we expect it to be sum 1, sum 2, sum 3, and then we run out of value, so it should return none. That should be the final value. So let's see that that is the case. Note that we needed to make v1 iter mutable. Calling the next method on iterator changes the internal state that the iterator uses to keep track of where it is in the sequence. We've dealt with this. If you've been with us since the beginning, or maybe you've watched on YouTube, you remember that going over the iterator actually consumes, it doesn't actually, like I'm sure we'll get into the details of what's actually happening, but it actually does modify it. And it almost felt like we were actually consuming the values, that we checked out the length. It was actually recording from the length of the position we were at to the end. And that was interesting. We didn't expect that. Coming from a language where we weren't doing iteration, like JavaScript, for example, we're doing mapping, filtering, reducing over an array. It returns a new array. I was interested to see that next is actually consuming or mutating the original iterator. But it makes sense. The iterator is designed to do that. So, and obviously it's a different concept than doing a function on an array or something in JavaScript. But that was cool. So that's what we're going to be talking about right now. So, and it says right here. So it modifies the internal state, right? In other words, this code consumes or uses up the iterator. That tripped us up. Each call to next eats up an item from the iterator. We didn't need to make v1 iter mutable when we used a for loop because the loop took ownership of v1 iter and made it mutable behind the scenes. That's a little confusing about this behind the scenes stuff, but whatever. Also note that the values we get from the calls to next are immutable references to the values in the vector. They are immutable references to the value in the vector. That's why we have the ampersand in front. Makes sense. The iter method produces an iterator over immutable references. If we want to create an iterator that takes ownership of v1 and returns own values that we can actually own, right? We can use into iter instead of iter. Similarly, if we want to iterate over mutable references, we can call iter mute instead of iter. So right now we're just getting references. If we want to own, we can do into iter. And if we want mutable ownership, right? We want mutable references, iter mute. Pretty cool. Methods that consume the iterator. The Iterator Trait has a number of different methods with default implementations provided by the standard library. You can find out about these methods by looking in the standard library API documentation for the Iterator Trait. Some of these methods call the next method in their definition, which is why you're required to implement the next method when implementing the Iterator Trait. Methods called next are called consuming adapters because calling them uses up the iterator. One example is the sum method, which takes ownership of the iterator and iterates through the items by repeatedly calling next, thus consuming the iterator. As it iterates through, it adds each item into a running total and returns the total when the iteration is complete. Again, with the tech decks, right? Here we have our vector. If we create an iterator, as we next, it's actually consuming them. So we're losing them, right? Whereas if we had something like a loop or something like an array in JavaScript, we would usually copy them. So we take it, right? And we create a new array, but we wouldn't modify the original, whereas iterator is consuming. So pretty cool to look at that. All right, so let's try Iterator Sum. Normally this is something like if we were dealing with an array with Python or JavaScript, this would be a great use case for reduce. We are just going to use the sum function, which is already built in. So let's write test and function Iterator Sum, and we do let v1 equal our classic 1, 2, 3. Let v1 iter equal v1.iter. Let total equal v1 iter.sum. So again, this is consuming. And then here we're just going to assert equal. Total should equal 6 because the total of 1, 2, and 3 is 6. Here it says cannot find value v1 iter in the scope. That's because I forgot the I here. No big deal. And here it's saying total. Type annotations needed. Consider giving total a type. And so here, that's because it could be an unsigned 32-bit integer. It could be a signed 32-bit integer. We're just going to do an unsigned 32-bit integer. All right. Let's run it. Get out of your way as usual. Cargo run. Everything passed. We didn't get any issues. Pretty good. We aren't allowed to use v1 iter after the call to sum because sum takes ownership of the iterator we call on it. Right? So we can't use v1 iter because sum is taking ownership. That's interesting. Okay. Methods that produce other iterators. Other methods defined on the Iterator trait, known as Iterator Adapters, allow you to change iterators into different kinds of iterators. You can chain multiple calls to Iterator Adapters to perform complex actions in a readable way. Because all iterators are, because all iterators are lazy, you have to call one of the consuming adapter methods to get results from calls to Iterator Adapters. Lot going on there. Just want to read that one more time. You can chain multiple calls to Iterator Adapters to perform complex actions in a readable way. But because all iterators are lazy, you have to call one of the consuming adapter methods to get results from calls to Iterator Adapters. Okay. Listing 1317 shows an example of calling the Iterator Adapter method map, which takes a closure to call on each item to produce a new iterator. The closure here creates a new iterator in which each item from the vector has been incremented by 1. However, this code produces a warning. This is what we're talking about. This is the tech debt, right? We go to function that flips. it's going to create a new iterator, right? I'm dropping stuff all over the place. Oh, man. But this is kind of, we're doing map, so we know that that returns a new iterator. So it says this returns a warning. Let's see what the warning is. First, let's go ahead and add it. We'll do a function Iterator Map Demo. All right. Test. And we'll just do let's v1 equal vec 1, 2, 3. And then we'll do v1.iter.map, and we're going to provide it the closure. We're going to increment it by 1. So we're going to take x, and we're going to return x plus 1. And here it says returns an iterator over slice, but it's yellow. Warning used. The map must be used. Unused map that must be used on by default iterators are lazy and do nothing unless consumed. So it gives you that warning. So check it out. We have that warning here. The code in 13.17 doesn't do anything. The closure we specified never gets called. The warning reminds us why. Iterator adapters are lazy, and we need to consume the iterator here. To fix this and consume the iterator, we'll use the collect method, which we used in chapter 12 with the end of args in listing 12.1. This method consumes the iterator and collects the results value into a collection data type. We've done this. We've done collect. And remember how cool it was, right? It inferred the type based on whatever type you specified the variable was. So really cool stuff. In listing 13.18, we collect the results of iterating over the iterator that's returned from the call to map into a vector. The vector will end up containing each item of the original vector incremented by 1. Let's try that out. So we're going to call .collect, and we're going to set that equal to v2. Now watch this. Notice I'm not specifying a type here. And so if I don't specify a type, it will say type annotation needed. Consider giving v2 a type. And that's because it needs to know how to collect, what type to collect into. Now I could provide that type here. So I could say, and actually, in fact, what I have to do is I just say, I believe it's like that. Like that. Something like that. Let's see. Collect from iterator self item. What does it complain about? Transform iterator into collection. Collect. Let's see. There is a way to do it without doing. Yeah, this is what I want. Collect a vector, obviously. So this is what I was trying to do here. So it's going to be a vector, right? A vector of that, and that's why I need that. And vector is not a thing. It's just vec. Duh. Okay, so what I do here. So this is now, it's going to infer the type here. And it says, warning, if this intentional prefix with an underscore, it's unused. But this is one way to specify the type that collect is going to return. But an easier way to do that is to use, I think they called it fishing or something. We're going to just specify it here. So we're going to say vec of I32. Pretty cool. And then what we'll do here is we will assert equal v2 vec, and we're going to assert it's equal to a vector with everything incremented by 1, and that's it. Pretty cool. Well, let's put these tests, because of course they're not actually, we can run them here. So that's pretty cool, right? We can run the tests like that. We could also move them in the main and they'll run themselves. But so here, so we ran this. You can see right here, I run the test and it passed. So we're all good. I can also, of course, move these into here. Let me copy these out. Why is that not working? Hold on. Let's see. And paste it down here. Oh, what did I do here? Actually, I modified everything. Oh, weird. I accidentally incremented. Interesting. Okay, so let's do this. Let me save these. So if I move these all into main, they would also run. I would just have to specify up here that we want to run tests. I forget what that looks like. Let me see. I believe it looks like, let's look here. It's automated tests. Config test. And then it would run it for us. But having it outside is nice because what we can do is we can just run them individually. So here, let me move out of the way, and you can see there, it's actually just running the test. I can click right here in my analyzer and it runs the test. So pretty cool. Great for things like this with the examples. All right, so let's move on. Let's pull this up here. All right, calling the map method to create a new iterator and then calling the collect method to consume the new iterator and create a vector. So that's what we're doing here. Because map takes a closure, we can specify any operation we want to perform on each item. This is a great example of how closures let you customize some behavior while reusing the iteration behavior for basically the iteration behavior that the iterator trait provides. So it allows us to provide, anything, right? We could provide any kind of function. So here we're doing +1, but we could do anything. We could modify, we could divide, we could do things. We can modify strings. We could create structs from each of them, right? It gives us a nice generic way to, it's a monadic operation, like functional, right? We talk about that, but really what it is, it gives us a way to transform these things. We give it a single function. It applies that function across everything in the iterator. So really cool. All right. Using closures that capture their environment. We did this. Same title. All right, let's see. Now that we've introduced iterators, we can demonstrate a common use of closures that capture their environment by using the filter iterator adapter. The filter method on an iterator takes a closure that takes each item from the iterator and returns a Boolean. If the closure returns true, the value will be included in the iterator produced by the filter. If the closure returns false, the value won't be included in the resulting iterator. Now, if you've used JavaScript, Python, you've definitely done something like this. I'm going to quickly pull it up just so we can hack on it real quick. Just because it's, I've done it so many times, it's so quick. Let's say I have a list. This is JavaScript again, but let's say const my list equals 1, 2, 3, 4, 5, 6, right? And I'm just doing it in JavaScript first so I can relate to the differences in Rust. And so let's say we want const only evens. What that would look like is my list.filter, and we return a Boolean. We want it to be only evens. So our filter is going to take a number, and we're just going to return num divided by 2. And we want it to equal 0, right? That means it's even. So we can just do not num divided by 2. Only evens. Oh, sorry. Actually, what we want to do is divided by 2 equal 0. Oh, I redefined it. Let's change that to const evens. Let's just call it evens. And there we go. There's our evens, right? We can get odds. I spelled odds wrong, but you get the idea. It'd actually be right? So that's how that would work in JavaScript. Let's see it now in Rust. All right. In listing 1319, we use filter with a closure that captures the shoe size variable from its environment to iterate over a collection of shoe struct instances. It will only return shoes that are the specified size. All right, let's try it. So yeah, we can write it right in our function here. Okay. Let's go up here and we will add the struct. So we're going to do derive, and we're going to have partial equality so we can do comparisons, right? And debug so we can use that nice syntax for printing things out. And we'll create a struct called shoe, and shoe has a size that's going to be an unsigned 32-bit integer. You can't have a negative shoe size. And the style is going to be a string. We're creating a function called shoes in my size. It's going to take shoes, which is going to be a vector of type shoe, a shoe size. Now that I'm like writing the word shoe over and over, it looks like such a weird word, right? Shoe. I don't know. Maybe I'm just weird. We know I am, right? And then it's going to return a vector of shoes, and of course it's going to be only the shoes in my size. I'm not going to reveal my size on stream. Come on. No, I can. 10.5. Pretty standard, I think. Yeah, pretty standard. It's hard. I know it's standard because when I try to find a shoe, it's like the first size that's gone. Y'all are taking that size. All right, shoes.intoiter .filter. So we're taking shoes, converting it to an iterator, calling filter on it. Filter, what is it going to take? It's going to take a closure. I'm going to call it shoe. I'm not going to call it S because I like to be a little more explicit. And we're going to do shoe.size equal shoe size, the one that's passed in, right? Then what are we going to do with it? We're going to collect it because we want to actually consume it, right? We want to, otherwise it's going to be, it's lazy, right? So collect is going to handle that for us. And no semicolon, leave that off because we're going to have an implicit return for that. Okay, now our tests. So here we have the config test, which is actually going to run the test. That's what I was looking for before. Mod tests. And what are we going to do? Use super. So that fancy stuff. We're going to write a test here. Filters by size. And the reason I'm not just copying and pasting is I like to get experience typing it. Like that's one of the ways I familiarize myself with the code, but of course you can copy and paste it. In fact, they include the buttons here. But yeah, feel free to speed it up if you want to skip this part, but I'm just going to basically type all this out. So let shoes equal vector. So we're creating a new vector. Shoe, and then we're gonna have one that's size 10. Yo, I know it's standard because it's, yo, look at that. There's two size 10s. Come on. How'd they know? They knew my size. Look at this. The book knew. Like, Tom, you have pretty standard feet, right? Style, string from, not saying you don't have standard feet if you have a different size. All, you know, all sizes are loved on this stream. Just don't worry about that. Don't even stress, right? All right, shoe. Size 13. So it's like we're starting to get in basketball territory, right? Those big sneakers. Style, so we'll do string from sandal. Not a sandal fan, not gonna lie. Not a sandal fan. Maybe it's because I have ugly feet. It is. Size 10, and then here what do we have? Boot. Yeah, I'm kind of a boot person. For sure. I like sneakers too. Comfy. All right. So let's go ahead and semicolon that off. And so now what are we gonna do? We're gonna say let in my size, right? We want to get only the ones in my size, and I'm gonna say size. Look, they knew my size. Come on, they knew my size, right? It's pretty cool. Equal shoes in my size. Shoes. We're gonna pass it shoes and size 10, obviously. And then we're going to assert equal. Now we can break this up. We can, move this out and say expected result. But we're just going to keep it all in the assert. And I'm going to copy this because I've written this plenty of times. And so here what we're saying is we will assert equal. So we expect that the result of calling shoes my size will be this vector with just the 2 that contain the size 10. And now what we'll do is we'll run this. Cargo run. I'm gonna get out of your way. I'm gonna switch up. I'm gonna go to the top left. It's been a while. And there you go, finish running. And actually, so you'll see it didn't actually run the test there. So what we'll do is we'll just run it here. Pretty cool, right? So running 1 test, filters by size. Okay, 1 passed, so we are all good to go. Pretty nice. All right, the shoes in my size function takes ownership of a vector of shoes. So let me keep this up over here. I'll try to, you know what, let me try to move. You know what I'll do? I'll keep it up. I'll keep scrolling it up so you have it as we read through. The shoes in my size function takes ownership of a vector of shoes. Right here, that's what this is, right? It's not a reference. It takes ownership of a vector of shoes and a shoe size as a parameter. It returns a vector containing only shoes of the specified size. So it takes ownership of shoes. And so we wouldn't be able to use shoes again after here. Like we wouldn't be able to use it in here because we gave ownership, right? In the body of shoes in my size, we call into iter to create an iterator that takes ownership of the vector. Then we call filter to adapt that iterator into a new iterator that only contains elements for which the closure returns true. What does that mean? We create an iterator from shoes. We then call filter. What do we want? We want a new iterator. What is the condition of the new iterator? It will only include items where when each item is passed to this function, it evaluates it true. What does that mean? I'm busting out the tech decks. Yes, I am. I'm doing it. I'm busting them out. What does it mean? We have 3 tech decks here. I'm going to say, let's do this. The ones that have blue wheels. I only want the ones with blue wheels, so I'm only going to take this one, right? If I wrote a filter function, I write a function that takes a tech deck skateboard and returns true if it has blue wheels. So I have that function. It's going to iterate over and check each one. Blue wheels? No. Don't include it. Blue wheels? No. Don't include it. Blue wheels? Yes. Include it. And so I get an iterator that contains only the value for which that function returned true. And that's how filter works. And that's why we call collect, because we actually want to consume it and return that. So pretty cool. I like it. The test shows that when we call shoes in my size, we get back only the shoes that have the same size we specified. Creating our own iterators with the Iterator trait. We've shown that you can create an iterator by calling iter, into iter, and itermute on a vector. You can create iterators from the other collection types in the standard library, such as hash map. It's pretty cool. You can also create iterators that do anything you want by implementing the Iterator trait on your own types. As previously mentioned, the only method you're required to provide a definition for is the next method. Once you've done that, you can use all other methods that have default implementation provided by the Iterator trait. That's pretty sweet. Basically, as long as you provide a way to get to the next thing, you can create an iterator. That's fantastic and very cool. So it's powerful. It's going to allow us to do some really cool stuff. We can create linked lists, right? We can create any kind of thing. It doesn't need to be a vector. That's pretty awesome. We can create a counter, just increments. You keep asking for next, just gives you the next number, right? 1, 2, 3, 4, 5, 6. I'll just keep going. 7, 8, right? Okay. So to demonstrate, let's create an iterator that will only ever count from. They stole my idea. I promise I didn't read ahead. I promise I didn't read ahead. Look at this. They stole my idea. It's fine. We'll use it. You heard it here, though. You heard me say it first. Right? Come on. All right. So we're going to create an iterator that only ever counts from 1 to 5. First, we'll create a struct to hold some values. Then we'll make the struct into an iterator by implementing the Iterator trait and using the values in that implementation. How do we implement the Iterator trait? We just need to implement that next function, right? So here we have the definition of the counter struct and an associated new function to create instances of counter. All right, I'm going to move these up top. So we got struct, counter, it's going to have a count, and the count's just going to be an unsigned 32-bit integer, because we're only going to count positive numbers here. The implementation of counter is we're going to implement a new function that's going to return, obviously, a counter. And what is it going to start with? 0. So counter, count, 0. And there we go. So we have a function there. Okay. Defining the counter struct is this here. The count struct has one field named count. Sorry, the counter struct has one field named count. This field holds an unsigned 32-bit value that will keep track of where we are in the process of iterating from 1 to 5. The count field is private because we want the implementation of counter to manage its value. We don't want to expose that. Instead, we're going to implement the next function to expose that via the iterator. So the next function enforces that the behavior of always starting new instances from the value of 0 in the count field, right? So it's going to enforce that. Next, we'll implement the iterator trait for our counter type by defining the body of the next function to specify what we want to happen when this iterator is used. So we're going to define the functionality of the next function. So we're going to implement iterator for counter type item equals unsigned 32-bit integer, right? And then here we're going to define the next function. Next, so it takes a mutable reference to self, and it's going to return an option self item, right? So it's either some or none. And so we're going to do a check. If it's less than 5, we'll return it. Otherwise, we'll return none. So if self.count less than 5, we're going to go ahead and return self. So first, we're going to increment self.count plus equal 1. And then we're going to return it wrapped in a sum. That's key, right? Otherwise, we're going to return none. So we have a proper option. I left off the semicolon, implicit return, right? Okay. We set the associated item type for our iterator to unsigned 32-bit integer, meaning that the iterator will return unsigned 32-bit integer values. Again, we don't worry about associated types yet. We'll cover them in chapter 19. We're going to be there before you know it, fam. We are. We want our iterator to add 1 to the current state. So we initialize count as 0, so it would return 1 first, right? If the value of count is less than 5, next we'll increment count and return the current value wrapped in the sum. So it'll wrap that in the sum. If it's less than 5, of course. Once the count is greater than 5, so once we start reaching the 6, 7 range, right, our iterator will stop incrementing count and always return none. So we know that we've run out. And a collect would not include the nuns, right? When you call collect, it discards them. Using our counter iterator's next method, once we've implemented the iterator trait, we have an iterator. So here it shows us how to demonstrate, it demonstrates how we actually use the functionality of counter. And we're going to use it by calling the next method on it directly, just as we did with the iterator we created back in 13.15. So here we're going to create a test. And we'll do function calling next directly. Let mute counter equal counter new. And again, it's going to start at 0. And then we're going to do, I'm going to copy this, but basically we're going to call .next on it a bunch of times. And we'll assert that it actually works as behavior. And so if I'm actually going to add 1 just to illustrate that it will continue to return none. So let's just add that there. It's just a nice thing to illustrate there. Okay, let me get out of your way, and let me run that. Again, nice thing I can run it here like this, and there we go. It passed. So what did we illustrate here? That in fact calling next on our counter does work and it returns the values wrapped in a sum. And I also just want to illustrate that once you call it, if it gets none, if you continue calling it, you'll still just get none as a response. So I just wanted to illustrate that there. All right. This test creates a new counter instance in the counter variable and then calls next repeatedly, verifying that we have implemented the behavior we want this iterator to have, returning the values from 1 to 5. Using other Iterator Trait methods. We implemented the Iterator Trait by defining the next method, so we can now use any Iterator Trait method's default implementation as defined in the standard library, because they all use the next method's functionality. That's badass, right? That's pretty sweet. So let's read that again. We implemented the Iterator Trait by defining the next, so we can now use any Iterator Trait. Okay, so we can now use any Iterator Traits method's default implementation as defined in the standard library because we've used next, and they use next behind the scenes. Awesome. For example, if for some reason we wanted to take the values produced by an instance of counter, pair them with the values produced by another counter instance after skipping the first value, multiply each pair together, keep only those values that are divisible by 3, and add all the resulting values together, we could do so. Yo. That's crazy. Let's walk through that again. I know they're doing it deliberately a little bit to confuse us, but let's do it again. For example, if for some reason we want to take all the values produced by an instance of counter, pair them with the values produced by another counter instance after skipping the first value, right? Skip the first value, pair them. Multiply each pair together, keep only those that are divisible by 3, and then add the results together. We could do so as shown in the test below. This is very cool. All right, let's make this test. This is pretty sweet. So we'll do our classic hashtag test function using other Iterator Trait methods. All right, let sum, it's going to return an unsigned 32-bit integer, equal counter new dot zip. We're going to see what this does in a second, and we're going to zip it with a counter new. We're going to skip the first value though. Dot map. So we're going to map. What does map do again? It's going to return an iterator of the same length, right? But it's going to allow us to modify each of the values. So we're going to map, and what we're going to do is going to take a tuple, because that's what zip is actually creating a tuple for us. And so we have A comma B, and we're just going to return A times B, so we're multiplying those pairs together. Then we're going to filter on those pairs, because now we have a single value, right? So we have our X value, which is the product. I don't even could call it product. And we're going to do product divided by product modulo 3, make sure it's divisible by 3. And then we're going to sum that. And then we're going to assert that this all equals, good thing they did the math for us. Pretty cool. So look, let's see what zip does. So you can see zip here is going to return an iterator of a tuple of unsigned 32-bit integers. Zips up two iterators into a single iterator of pairs. So it matches them up together, right? And then that's how we end up with this tuple here as the input of our map function here. We then create the product, and then we filter on that, and we end up with this here. And what does it say here? Map, what is it saying? Let's see. Counter new, zip counter new, skip 1. Why is map sad? Takes a closure, blah, blah, map. Okay, wait, let me save. Let me run this, see what happens. Expected closure that takes a single two tuple as an argument. I didn't wrap it. It's got to be a tuple, not two arguments. So there we go. All right, now let's try running that test. Awesome, we passed. We're all good. So pretty cool. I think that's pretty awesome. Note that the zip produces only 4 pairs. The theoretical 5th pair is 5 none is never produced because zip returns none when either of its input iterators return none. That's interesting. That's why you skipped the 1 to get it to not match up directly. All these method calls are possible because we specified how the next method works, and the standard library provides default implementations for other methods that call next. Improving our IO projects. We can go back and improve our grep project. Awesome. I think we'll have time to get through this. With this new knowledge about iterators, we can improve the IO project we did in Chapter 12 by using iterators to make places in the code clearer and more concise. Let's look at how iterators can improve our implementation of the config new function and the search function. All right, I'm going to go ahead and pull that up. So let's ditch that. All right, so that was Chapter 12, I believe. Yep, mini grep. I'm going to open up mini grep. Awesome. Grab a sip of water. All right. So remember, all of our logic is in our lib function here. Okay, so removing a clone using an iterator. In listing 12.6, we added code that took a slice of string values and created an instance of the config struct by indexing into the slice and cloning the values, allowing the config struct to own those values. In listing 13.24, we've reproduced the implementation of config new function as it was in listing 12.23. So we should have this somewhere. So let's pull that up. Up here, implementation config. So again, if len less than 3, return an error. Otherwise, we made some changes ourselves. We made some changes when we were doing the case insensitivity, but the general gist is the same. We're doing indexing string and we're cloning. At the time, we said not to worry about the inefficient clone calls because we would remove them in the future. Well, that time is now. Wow. I was looking forward to this moment. I'm just saying. We need a clone here because we have a slice with string elements in the parameter args. But the new function doesn't own args. So let's just go over that again. So we need a clone here because we have a slice with string elements in the parameter args, right? Parameter args, slice with string elements. But the new function doesn't own args. To return ownership of a config instance, we had to clone the values from the query and file name fields of config so the config instance can have its own values, right? Because it doesn't own the args. They're separate. They're part of a separate process, right? They're part of the main. With our new knowledge about iterators, we can change the new function to take ownership of an iterator as an argument instead of borrowing a slice. We'll use the iterator functionality instead of the code that checks the length of the slice and indices into specific locations. This will clarify what the config new function is doing because the iterator will access the values. Once config new takes ownership of the iterator and stops using indexing operations that borrow, we can move the string values from the iterator into config rather than calling clone and making new allocation. All right, that's a lot, but what does it mean? So using the returned iterator directly. Open your IO project's main RS file, which should look like this. Let's see. Similar. We have, so it looks like this, yep. We'll change the start of the main function that we had in listing 12.24 to the code below. It won't compile until we update config new as well. All right, so here we have config new, and instead of passing it args like this, we're going to pass it env args directly. Env args. So here we can get rid of that. And nothing else has changed, so we'll just leave it at that. The envarg functions returns an iterator, and that's why we were calling collect on it before, right? Rather than collecting the iterator values into a vector and then passing a slice to the config new, we're now just passing ownership of the iterator returned from envargs to config new directly. And we'll let config new handle its use case of it. Next, we'll need to update the definition of config new in your iOS project to support that. So if you look here, it's saying mismatch types, right? And so now we got to update the type of config new. So instead of expecting a slice of string, right, we're going to modify this to accept the env args directly. And what does that look like? Well, env args, and we want it to be mutable. We'll need to update the definition. Let's change the signature of config new to look like the below. It still won't compile because we have to update the function body, but here's the signature. The standard library documentation for envargs function shows that the type of the iterator it returns is standard envargs. We've updated the signature of config new function so the parameter args has the type standard envargs instead of a string slice, right? Or a part of a vector. Because we're taking ownership of args and we'll be mutating args by iterating over it, we can add the mute keyword into the specification of args parameter to make it mutable. Okay, how do we know it returned envargs? Well, we can actually just hover here, or you can look here and see that this returns args, and you can actually hover over this bit, and you can see returns standard env args, right? So pretty cool. Okay. Oh, I accidentally closed it. Back in action. Okay, so we need to update now this next part. So let's see what they did here. So next we'll fix the body of config new. The standard library documentation also mentions the standard new args implements the iterator trait. Args implements the iterator trait. So we know it has a next function that we can call. So let's try doing that. All right, so here we're gonna do query is args.next. And we need to do a match because it's an option, right? Match, and we'll do sum arg, and we'll set this equal to the arg. Otherwise, we'll throw an error, none, return error, and we'll copy whatever it says. Didn't get a query string. Awesome. And same thing here. We'll do .next, make that a match. We're gonna do pattern matching, right? And if we have some arg, we'll go ahead and return that arg. Otherwise, if we have none, we'll go ahead and return an error. What are we gonna say? We're gonna say didn't a file name. Cool. Have a semicolon on here. Here's something also where we've made a change in the code that isn't in the other code, so we're gonna also change this here. So what we'll do is we'll say let case sensitivity arg equal args oh, actually, you know what we can do? We can move this logic. So what we'll do is we'll actually take this here. You know what we'll do? So we'll do it like this. We'll say let case sensitive equal. This is actually much nicer. So what we can do is we can say args.next, and we'll match on that. And if there's none, a match, right? If we get some arg, right, we'll set it equal to arg, as we usually do. So case sensitive is the arg, right? Actually, we want to pass it to this. So we want to pass it to parse case sensitive arg. Otherwise, if it's none, what is our fallback? If it's none, we use this, right? Oh. So that's pretty cool. So if it's some arg, we use it. Otherwise, we use this. And now we can get rid of this part. All right, awesome. Okay, so what do we do now? Remember that the first value in the return value of envargs is the name of the program. We want to ignore that and get the next value. So we first call next and do nothing. Ah, I didn't see that part. So they call next up here. That's so we can skip over And what I'm going to do is I'm actually going to, oh, we don't even need to do the check anymore. We can do that, you know, it's going to handle it based on the arguments that we give it. So I'm going to put a comment that says the first value of env args is the name of the program. So we will skip over that by calling next right away. I like to just put these types of things in the code because, you know, later I'll wonder, hey, why did I do this call to next? And if I got rid of it, we'd have a real issue, right? So I like to put those comments. I think it's good practice. So we call next, so it does nothing with the return value. Second, we call next to get the value we want to put in the query field. If next returns a sum, we use the match. If it returns a none, we report an error. Making the code clear with Iterator Adapters. We can also take advantage of the iterators in the search function in our IO project. So first I want to test that this still works. So what I'm going to do is I'm going to run cargo run. And if I run it like this, it's going to say, oh, well, actually, hold on, let me go into minigrep first. If I run cargo run, didn't get a query string, so good, we got that error. So I'll do cargo run and I'm going to put a poem.txt. And there we go. And I'm going to say insensitive. And there it ran case insensitive. And if I say sensitive, it ran it sensitive. And if I give it nonsense, it ran it sensitive. So it worked. So pretty cool. All right, so we're still good. Everything still works. And I believe I have tests, so I can run cargo test to test. And yeah, we still have our tests, so we're good. We'll leverage that. That's like we're doing TDD, right? We can refactor and lean on the tests that we wrote. So pretty cool. Okay, so we can write this code in a more concise way using Iterator Adapter methods. Doing so also lets us avoid having mutable intermediate result vector. So that'd be kind of cool. So first, this is our search code, so let's look at it. So our search code takes a string slice and contents, and basically we parse the contents and we try to find if it contains what we're searching for, and if it does, we push it onto a vector that we then return. Okay, so we can write this code in a more concise way using the Iterator Adapter methods. Doing so also lets us avoid having mutable intermediate results vector. The functional programming style prefers to minimize the amount of mutable state to make code clearer. Removing the mutable state might enable a future enhancement to make searching happen in parallel, because we wouldn't have to manage concurrent accesses to the results vector. Shows this change. Awesome. Let's try it out. All right. So we're going to do a little change here. So let's comment this out. And what we'll do is what they have us doing here. So we'll do, let me move over here, there, so you can see it, right? Okay. So we'll do contents, and we're just going to do an implicit return here. Dot lines, going to grab the lines, right? And what does that return? It returns an iterator over the lines of a string. So we have an iterator. We're going to filter on that, and we only want the lines, right? Because our iterators can be each line. So we're given a line. And what do we want? We want only the lines that contain the query. And what does that return? Returns true. Oh, well, the filter returns. Creates an iterator, and it's going to be only things that match, right? And now we're just going to collect that. And what we can do is we can run our test to make sure we haven't broken anything. And there we go. We're still good. Doing a little TDD, right? Recall that the purpose of the search function is to return all lines of the contents that contain the query. Similar to the similar to the filter example in 1310, the code uses the filter adapter to keep only the lines that lines.contain query returns true for, right? When we collect the matching lines into another vector with collect, that's what collect's going to do. It's much simpler. Feel free to make the same change to use iterator methods in the search case insensitive function as well. All right, let's do that. That's a great idea. So for search case insensitive, we can comment this out. And so here what we'll do, it's very similar. We're going to do contents dot lines dot filter, and this is going to be slightly different because we're going to do line, and here we're just going to do line dot to lowercase dot contains query dot to lowercase. Just comparing them to lowercase. And then we're just going to do dot collect. And let's go ahead and we save that, and I'm just going to run my test to make sure everything still works. And nope, we have an issue here. We got to consider borrowing here because of the fact that we have that there. So you can see here it says expected, consider borrowing here. So expected standard mutable character, closure found standard string. Consider borrowing here. So let's do that, right? And let's run our test. And we're all good. So we grab the reference to it so that we can modify. We do to lowercase here, right? And we are all set. And just so we can clear it, I'm just going to run it cargo run poem. There we go. Insensitive, sensitive by default. There we go. Pretty cool. All right. The next logical question is, which style should you choose in your own code and why? The original implementation listing 1328 or the version using iterators in listing 1329. Most Rust programmers prefer to use the iterator style. It's a bit tougher to get the hang of at first, but once you get a feel for the various iterator adapters and what they do, iterators can be easier to understand. Instead of fiddling with the various bits of looping and building new vectors, the code focuses on the high-level objective of the loop. This abstracts away some of the commonplace code, so it's easier to see the concepts that are unique to this code, such as the filtering condition each element in the iterator must pass. But are the two implementations truly equivalent? The intuitive assumption might be that the more low-level loop will be faster. Let's talk about performance. So just really quickly, I definitely prefer the iterator way. I'm sure everyone will be a little bit different, but I like the iterator way because I like to read it like a list of steps, right? So we have the lines, we filter, we collect. The other way is also pretty readable, but it's nice. And one thing that we could also do is, we could pull this out and define this separately. We could say create a comparator function and pass it and name it and pass it here. That'd be fine too. And then you can so we could do something like this. That's what I'm thinking. Something like let find query. You could do this, find query or is query in line. And you can set that equal to this, right? And then you could just pass that here. That's like another way to handle this case here. What is it saying about line? Type annotations needed. So, for this we just say line is, this is gonna return a bool. And line is a string. Slice, actually. I believe it's a string slice. What is line? Let's see what it's complaining about. Type annotation needed. Type must be known at this point. Oh. Yeah, it doesn't know because of course it's coming off a filter. So that's why we do it there in line, because it'll infer the type. Otherwise we'd have to predefine it. So that's a good use case for keeping it in line, I guess. Either way is fine. I'm sure we can get it to work either way. But yeah, it knows the type here because of that. So interesting. I'm glad we tried that. Okay, performance. And this is where we'll wrap up. Comparing performance loops versus iterators. I know if anyone has gotten into performance before, it can be a little bit difficult to talk about it. Like in some cases we talk about big O and things like that, but there's always trade-offs, right? So we're going to read a little bit about that. To determine whether to use loops or iterators, you need to know which version of our search function is faster, the version with an explicit for loop of the version with, or the version with iterators. So the for loop with iterators. We ran a benchmark by loading the entire contents of The Adventures of Sherlock Holmes by Sir Arthur Conan Doyle into a string and looking for the word the in the contents. Here are the results of the benchmark on the version of search using the for loop and the version using iterators. For loop, iterators. So the iterated version was slightly faster. We won't explain the benchmark code here because the point is not to prove that the two versions are equivalent, but to get a general sense of how these two implementations compare performance-wise. For more comprehensive benchmark, you should check using various texts of various sizes in the contents, different words and words of different lengths as the query, and all kinds of other variations. The point is, iterators, although a high-level abstraction, get compiled down to roughly the same code as if you've written the lower-level code yourself. Iterators are one of Rust's zero-cost abstractions, by which you mean using the abstraction poses no additional runtime overhead. This is analogous to how Bjorn Stroustrup, the original designer and implementer of C++, defined zero overhead in Foundations of C++, 2012. In general, C++ implementations obey the zero overhead principle. What you don't use, you don't pay for. And further, what you do use, you couldn't hand code any better. Interesting. As another example, the following code is taken from an audio decoder. The decoding algorithm uses the linear prediction mathematical operation to estimate future values based on linear function of the previous samples. This code uses an iterator chain to do some math on 3 variables in a scope: a buffer slice of data, an array of 12 coefficients, and an amount by which to shift data in QLP shift. We've declared the variables within this example, but not given them any values. Although this code doesn't have much meaning outside of its context, it's still a concise real-world example of how Rust translates high-level ideas into low-level code. To calculate the value of prediction, this code iterates through each of the 12 values in coefficients and uses the zip method to pair the coefficient values with the previous 12 values. So not too important about what's going on, but we can see the zip here is happening with the prediction versus the coefficients, right? Then, for each pair, we multiply the values together, sum all the results, and shift the bits in the sum QLP shift bits to the right. So similar to what we did before, right, where we mapped and then summed. Calculations in applications like audio decoders often prioritize performance most highly. Here, we're creating an iterator, using 2 adapters, and then consuming the value. What assembly code would this Rust code compile to? Well, as of this writing, it compiles down to the same assembly you'd write by hand. There's no loop at all corresponding to the iteration over the values and coefficients. Rust knows that there are 12 iterators, so it unrolls the loop. Unrolling is an optimization that removes the overhead of the loop controlling code and instead generates repetitive code for each iteration of the loop. That's pretty cool. All of the coefficients get stored in registers, which means accessing the values is very fast. There are no bound checks on the array access at runtime. All these optimizations that Rust is able to apply, making the resulting code extremely efficient. Now that you know this, you can use iterators and closures without fear. They make code seem like it's higher level, but don't impose any runtime penalty for doing so. So basically all that to say, we can safely use iterators. We're not going to impact the performance. It's still going to remain fast and slick as hell because Rust is savage, right? It's doing some awesome stuff. That's fantastic. Really cool. And I definitely prefer the iterator way, so I'm happy about that. Closures and iterators are Rust features inspired by functional programming language ideas. They contribute to Rust's capability to clearly express high-level ideas at low-level performance. The implementations of closures and iterators are such that runtime performance is not affected. This is part of Rust's goal to strive to provide zero-cost abstractions. Now that we've improved the expressiveness of our I/O project, let's look at some more features of Cargo that will help us share the project with the world. All right, so we are just at about 10:50, so we're going to call it there at that end of that chapter, and we'll start, I believe, the next chapter. Yeah, we'll start chapter 14 next week. So, awesome. Thank you for everyone who hung out in the chat. It was really cool. We got to use iterators and closures. I'll post all this code up on GitHub. As always, that gets posted. Let me pull that up here. let's see, GitHub/TomAGirl. You can find that. You can see that here, right there. My GitHub URL on the bottom right. So GitHub/TomAGirl. I posted to the Learn Rust Live if you want to pull down the code. As always, if you join late or you missed part of the video, do not worry. All the videos get posted to YouTube. You might be watching it on YouTube right now. Who knows? So we have all the chapters from 1 to 12 that we've covered so far. I'll be putting chapter 13 up there as well as some one-off videos like learning Rust development with a Docker container. You can have a Docker Compose environment to run Rust code if you don't feel like installing it on your machine, and as well as other videos. So check that out. Subscribe if you like what you see. I really appreciate it. Also, feel free to throw some comments on. We've gotten amazing comments, so happy to answer any questions. And just thank you so much for everyone that's been supporting the stream and supporting the YouTube channel and adding those comments. It's really been humbling to see how many people watch the videos and get value out of it. So happy to be contributing there and glad I can help. And I love seeing people join in the Rust adventure with me. Also follow me on Twitter and you'll get updates for when I go live. Again, just want to give a shout out to Steve Klobnik, Carol Nichols, and the folks in the Rust community who've created the book that have allowed us to progress this far in our Rust learning and becoming Rustations. We've come very far. If you've been following on the stream and watching on YouTube, you know we've come pretty far. We've done chapters 1 through 13 now of the book. We've done all of the Rustlings exercises. So it's been fantastic. We're going to keep going with it. But again, I just want to give a shout out to anyone who's been supporting the stream, supporting the YouTube channel. It's been a lot of fun seeing the comments and just seeing people, happy about and excited about what we've been doing. So keep it up. Again, Tuesdays, 9 p.m. to 11 p.m. Eastern time on Twitch if you want to catch it live. Otherwise, on YouTube, it's usually uploaded the following Wednesday. Sometimes I'm kind of late with it and I get it up there on Thursday, but keep an eye out. Again, shout out to all the Rustations. Everybody have a great night. I'll catch you next week.